Okay, I think we can get started. Hi, everyone, again. So I'm going to give a small introduction about our speaker for today. First of all, how do I pronounce your name?
My name is Phan.
Phan. Okay. Yes. So welcome. Phan received her PhD in computer science at the University of Massachusetts, Amherst, in February 2022. She's advised by Professor Eric Miller. She is interested in methods for learning with limited data, including causal reference, neurosymbolic learning, and reinforcement learning. Phan has previously worked on confidence intervals for small samples, causal inference, and multi-armed bandits. She's giving today's talk on practical mean bound for small samples.
Yeah.
I will let you go ahead and start.
Okay, thank you very much for the introduction. So hi everyone. So today I'm giving a talk for finding confidence interval for small sample. Can you enable me to share my screen?
Yes, let me do that. Can you try now?
Sure. Yeah, so my talk today is about towards practical mean bound for small samples. So this is joint work with Professor Philip Thomas and Eric Miller at UMass. And it was accepted as a paper in ICML 2021. So first, I will talk about the problem statement, our algorithm, the theoretical results, and the simulation result. So first is a problem statement. So we consider the classic problem of finding a non-parametric upper confidence bound for the mean of a distribution given a sample. So to be more precise, we only assume that the distribution has support, which is a subset of a bounded interval. And given the confidence level, we want to find an upper confidence bound such that the probability that the upper confidence bound is larger than the true means is at least 1 minus alpha. Can you see my mouse?
Yeah, we can see the cursor.
Okay, thank you. So typically alpha is small. So for example, like 0.05. So in that case, we will want to find a 0.95 confidence interval upper bound. So I will talk about existing result and why we are interested in this problem. So there are many existing confidence bound for the mean of the distribution we support on the interval from 0 to 1, but they fall into two categories. So the first one is confidence interval with guarantee, but they do not, they have bad performance for small sample. So bound in this category include Maurer and Pontin, Hoeffding, and Anderson. So in the plot over here, I plot the expected value of these bounds versus the sample size from 0 to 50. And the purple line is Maurer and Pontin, the green line Hoeffding, and the red line is Anderson's bound. And the solid black line is the true mean of the distribution. So here I plot for three distributions, beta 1,5, uniform, and beta 5,1. And then you can see that this bound produce values that is quite far away from the true mean, so which suggests that they are loose. So the second type of bounds is that they don't have any guarantees, but they have good performance for small samples. So one example is student T. So here the same, here I plot the alpha quantile value of the bounds with the sample size. So if the alpha quantile value of the bounds is below the true mean, that means that the algorithm, the bounds produce a value that is smaller than the true mean for alpha per alpha portion, more than alpha portion of the samples, which means that they don't have guaranteed coverage. So here you can see that for Maurer-Pontin, Hoeffding, and Anderson have the alpha quantile value of the bound is above the true means, but for student T, the alpha quantile value of the bound is below the true mean for this sample size. So which means that they don't have guaranteed coverage. However, I'm come back to the previous picture. So this is the expected value of the bound. So the expected value of student D actually quite good. It's very close to the true mean, which means it's very tight. So why do we care about the problem of finding mean bound for small samples? So in practice, there exists some scenario where small samples are important. So one case is phase 1 clinical trial where only a small number of people are recruited to conduct the test. Another example is when the problem involves an important weighted estimator. So for example, in safety enforcement learning, people use important weighted estimator to estimate to bound the expected policies return. And here I plot the distribution of the sample mean of an important weighted estimator. So here the source distribution is Gaussian and the target distribution is beta for 1. And then you can see here that the sample mean distribution is very skewed, even for large sample size. So which means that it's generally not a good idea to apply student T, because student T assumes that the sample mean is converged to a Gaussian to a T distribution. So here come our problem statement. So we want to find a trade-off between these two types of confidence interval. So we want to find an upper confidence bound that so that it has guaranteed coverage for distribution on 0, 1, but it also have good performance for small sample size. So here I will describe our bound. Is anyone having any question about the problem statement? Okay, I will go ahead and describe our algorithm. So our bound is take some parameter as an input. So I will go through them, and then so first is the input is a sample. So the sample, the bold letter denote a sample. So X is a sample of size n. A confidence level alpha. So alpha is typically small, like for example 0.1 or 0.05. And here is a function or sometimes called a statistic T of the sample. So for example, T can be the sample mean of X, but our bound could take any statistic T. And given these three parameters, we output an upper confidence bound, B alpha dt of X. So I will explain the role of the statistic T. So T defines the order of the bound. So for example, if T of X is smaller than T of Y, where X and Y are two samples, then our bound will output the value such that the upper bound for X is smaller than B of Y. So as a side note, so Hoeffding order the samples by the sample mean. But we can produce a guarantee bound with any function T. So here I will go into detail about describing our algorithm. So first I will have to describe some notation. So here on the left hand side in figure A, I have a step function which we call G. And here, this is a function of the sample X and the vector L value. So the sample X, the order statistic of the sample X is plot in the X-axis. So here X1 is smaller than X2 and it's smaller than X3 and so on. And L is a vector value. L is a value vector between is a vector value between 0 and 1, and here the order statistic of L is plotted on the y-axis. So L1 is smaller than L2, is smaller than L3, and then using these for any two vectors, I can plot the step function G like this. So if L is, for example, if L is a CDF, then this step function corresponds to a CDF, the CDF of a discrete random variable with support on x1 and until x5, and then the MXL is a mean of that distribution with this CDF GXL. So this is the mean of the, so if you imagine this blue step function here CDF, then MXL is a mean of this blue CDF. And on the right hand side, I plot the CDF of a distribution F in red. So and x1 until x5 is a sample of distribution, is a sample taken from distribution F. And then if I take F of x1 to be L1, F of x2 and to be L2, then I can also plot the blue step function, which is similar to the one on the left hand side. And if here's the only thing we need to remember is that, so if we let mu to be the mean of the distribution with CDF, with the red CDF, and Fx is the mean of the blue distribution, the distribution with the blue CDF, then this the mean of the blue CDF is larger than the mean of the red CDF. So this is true because as you can see, there's a blue CDF push the mass toward the higher support, the support with higher value. So it puts the mass to the right hand side. So which means that is why the mean of the blue CDF is larger than the mean of the red CDF. And here I will explain the main idea behind the algorithm. So so this algorithm is visual. So it can be, the proof can actually be sort of described in picture, but it's look a bit evolved. But I will can come back to this after at the end of the talk if it's not very clear and anyone else has some question. So this so here I have 4 pictures. So here, if you can imagine that let's X be the sample with the largest sample with the largest value of Tx such that the bound fails. So remember that our bound order sample by T. So which means that as T of X increase, the value of the bound will increase. So we are finding an upper confidence bound, which means that when T is small, and when T of X is small, then B of X will be small, and therefore it's smaller than the true mean. So the bound will fail for X with the small b of X, and which correspond to small t of X. So we want to say that the probability that the bound fail is almost alpha. So then with that mean that our bound has guaranteed coverage. And that is equivalent to say that the probability of T of Y such that T of Y is smaller than T of X is smaller than alpha. So here on the top left figure, I plot the region of sample Y so that T of Y is smaller than T of X. So the x-axis, so here I assume the sample size is 2. So example only consider example X or Y only consider 2 value X1 and X2 or like Y1 and Y2. And here I plot the order statistic of these samples. So which is why Y2 is always larger than Y1. So which means, so that's why we only consider the region above the diagonal. And suppose, for example, actually T is linear. then the region where t of y is smaller than t of x is this yellow triangle. So for example, if t is a sample mean, then this yellow triangle is a region where y1 plus y2 is smaller than x1 plus x2. So we want to say that the probability of sample fall into this yellow region is at most alpha. So the probability of the yellow region is most alpha. So here if I do a transformation, u equal to f of y, then I arrive at the sample on the top right corner. So here the x-axis and the y-axis become u1 and u2, where u is f of y. And the yellow regions become this, the yellow triangle becomes this sort of like yellow region where it's no longer, the boundary here is no longer linear. So we want to say that the probability u fall into this yellow region is also as most alpha. And then how do we, so next, in the next step, we will try to upper bound the yellow region. So the reason that we do this transformation step u equal to f of y is because of this well-known property that if you for any sample from a continuous distribution, if you consider the CDF of the sample, then the CDF is uniformly distributed. So this is, for example, if you take sample from let's say a Gaussian distribution, and then you consider x is Gaussianly distributed, and then you consider f of x, then f of x is uniformly distributed on the interval from 0 to 1. So we say no matter what x is, f of x had a known distribution. So when we do this transformation, then u here we see like f of y will be uniformly distributed. And then we will also want to know whether if you take a sample from the uniformly distributed distribution, the probability that it falls into this yellow region is most alpha. So the advantage of doing this transformation is that here we don't know the distribution of y, but here we know the distribution of u. We know that it's uniform. Okay, so now the question becomes, given the uniformly distributed u, what is the probability it fall into this yellow region? And then we will to do that, I will upper bound this yellow region, and then say that the probability of the region that's cover this yellow region is most alpha. So the way I upper bound this yellow region is that I divide this yellow region into many the union of many small rectangle. So for example, if I take any point here, I can draw a parallel line here and then a parallel line here to make it a rectangle, and then the union of many sub rectangle will be the yellow region. So now I will upper bound the any separate rectangle. And then when I take the union of all of these upper bound, I will have a union of this, I will have an upper bound of this yellow region. So here is how I upper bound the rectangle. So for any separate rectangle, so recall that u here is an uniformly distributed random variable, and then we want to upper bound the probability that it will fall into this yellow rectangle. So because this is a rectangle, so if you take this point and then you draw a straight line, then the yellow region will be below the green line, below the straight line. So which means that the probability that u is inside the yellow region can be upper bounded by the probability that u is below this green line. And here I take the green line to be I take the green line to be any linear function. So, but like, so this is true for any linear function, but here I use a specific linear function, which is myu equal to myfy. So recall here that y is the point here. And then myu is the induced mean we talked about earlier in the previous slide. So just as a reminder, so XL is the mean of the distribution, which is blue CDF, and easy linear because users add up those x1 times L1 plus x2 times L2 minus L1 plus x3 times L3 minus L2. So this MXL value is linear in both x and y. So here, because it's a linear function, so I take advantage of it, and then I plot the line MYU, which is linear in U, and U is a variable here, equal to M of Y Fy, which means I have a green line. And in the next step, I up above this green, the region below this green line by the region below the red line. So the red line is MYU equal to mu. So the reason I can do it is because we have the right hand side MY Fy is always larger than mu. So if I substitute this, if I shift this green line a distance above, then I will have a red line that is like that can up above the green line. So we call this is true because of this property. So the mean of the blue CDF is always larger than the mean of the red CDF. So M of x Fx is larger than or equal to mu. So because of that, then this the right hand side of this green line will always be larger than the right hand side of the red line. So that's why the red line will be above the green line. So this means that the yellow rectangle will be covered by the region, this region under the red string line. So recall this, I can take I can divide the yellow region over here as a many rectangle, and then for each rectangle I draw a green line and the red line. So it will become the figure in the right hand, the bottom right of the picture over here. So so that means that the yellow region here will be bounded by all of the by the region under all of this green line. And then the region under all of this green line will be up above by the region under all of the red line, which is this region. So I have shown that the yellow region will be up bounded by the line, by the region below the red line. So mathematically, so here we consider the yellow region is a probability that sample y have t of y smaller than t of x, where x is the input sample and y is a random variable. And then when we do the transformation to U, this red region is actually the probability such that MYU is larger than the true mean. The union of all U such that U is in this yellow region satisfy MYU is larger than the true mean. This is a red region. And then I just rewrite the union sample by the supremum symbol, by the supremum symbol. So this is equal to this this random variable. The probability that this random variable is larger than mu. And then we want this probability to be recall that we want to say that this probability is at most alpha, because we want to say that the probability that the bound field is at most alpha, which means that we want to say that the probability the sample U in the yellow region is at most alpha. And we are doing that by saying that the probability that the sample U fall into the red region is at most alpha. But so if you look at this equation, this is just a probability of some the right hand side is a constant, and then the left hand side is a random variable. So we actually want to say that the probability that a random variable is larger than mu is at most alpha. So this will be true if the 1 minus quanta alpha quantile of that random variable is smaller than the constant here. However, the one minus one, so the one minus, so if we define this one minus alpha quanti of this random variable to be b of x, then this statement is true by assumption, because here we assume that b of x is smaller than mu. So that is a design of the process that I designed this bound. So if we want to this properties about phi to be equal smaller than alpha, this is true if the one minus alpha quanti of this random variable is smaller than mu. So if we define the value of the bound to be the one minus alpha quanti of this random variable, then this assumption will actually be satisfied by definition. And yeah, so one of the interesting thing about this approach is that you can use any statistic t as an input. So this bound will satisfy that the bound for any statistic t, this we will always show that the property of this yellow region is most alpha. So and then our bound will order our algorithm here will output a bound that order the sample by t. So t could be anything, that it could be the sample mean, it could be some very strange thing like a L2 norm, and it could be the maximum value of the in the sample, it could be the minimum value of the sample. Then our bound will always have guarantee, but with different form of performance. Yeah, so here is also a description of the algorithm. So we sample U from a uniform distribution. So U is a sample of psi n from the uniform distribution, and then we compute this value in the previous slide. So it is the super amount of on y in the yellow region of MYU, and we output the one minus alpha quanti of this value at the bound. So this green guy here is the same green symbol in the previous slide. So how computable this bound is, it depends on how whether you can compute this value. So so recall that MYU here is a linear function, and then so for example, if t is a linear function, then this problem is a linear optimization problem, and this is very easy to solve. If t is in some other cases, for example, if t is a L2 norm, then you also have a optimization problem where you are optimizing a linear constraint over the quadratic objective, and this can also be solved. In general, it's not always true. So for example, if I define t to be something very weird, like psi of x1 plus psi of x2, for example, or like I can define t to be some function that is defined by a neural network, for example, then you are optimizing a linear function over this direction, and then it's not always solvable. So I will show some theoretical guarantee and then some simulation results. So our theoretical results, so we show that our bound may have guaranteed coverage, and we also show that for some specificity it has good performance. So what is good performance here? So for any sample size, and then for any confidence level alpha, and for any sample x, then our bound is smaller than equal to Anderson's bound. So Anderson's bound is not very well known, but is actually always smaller than or equal to Hoeffding for any sample. So which means that for any sample size and for any alpha, and then for any sample x, our bound is smaller than or equal to Hoeffding for any sample. So this is not only in expectation, but like for any x, our b of x is smaller than or equal to Hoeffding of x. And I will talk a little bit about the computation results. So here, yeah, so we have to there's two computation issues that we need to resolve. So the first thing is like we need to solve the optimization problem, which I talked about in the previous slide. The other issue is that we need to compute the one minus alpha quanti of a random variable. So we use Monte Carlo simulation to compute the 1 minus alpha quantile. And then we can prove that the Monte Carlo output will converge to the theoretical value of the bound if we increase the number of Monte Carlo samples. And we also show that given any error threshold epsilon, we can compute the number of Monte Carlo samples such that the value of the Monte Carlo estimation is larger than the true mean with probability 1 minus alpha, and also epsilon close to the theoretical value of the bound. And so for the time, if for small sample, if you compute the bound for one time for, let's say, sample size 50, it takes like seconds in the normal computer. And another thing to note is that the bound outputs the same value for any sample with the same t of x. Therefore, we can also pre-compute a table mapping t of x to the value of the bound. And then the next time you can just take the value from the table without having to compute it again. And here, so I will show some simulation result. So this is the same figure I showed at the beginning of the talk. So here we plot the three. We compare our bound to other bound Hoeffding, Maurer and Fontaine, Anderson, and student T. So recall that the three bound here, Maurer and Fontaine, which is the purple line, Hoeffding, which is a green line, and Anderson, which is a red line. These three dash bound are the bound with in dash line are the bound with guaranteed coverage, but with loose performance. And the dot line here is student T. So this bound does not have guaranteed coverage, but it has very good performance because it is very close to the true mean. And the solid black line here is the true mean of the distribution. So our goal is that we want to have something in between these bounds in the dash line and student T. So here we plot the performance of our bound with two different T. So one is like T is equal to Anderson's bound, and one is T is equal to the L2 norm of the L2 norm of the sample. So the yellow line and the green line are these two bounds. So as you can see, the expected value of our bound is in between student T and the three dashed line for these three distributions. So which means that each solver provide a trade-off between these bound, existing bound with guarantee and student T which does not have guarantee. So we also plot the alpha quantile value of the bound. So so if the alpha quantile value of the bound is below the true mean, that means that the bounds do not have guaranteed coverage because it will output a value that is smaller than the true mean for more than alpha portion of the sample. So here you can see that student T, the alpha quantile of student T is fall below the true mean, so which means that it does not have guaranteed coverage. And but the alpha quantile on this bound, the Maurer and Fontaine, Hoeffding, Anderson, and our two new bounds is above the true mean for all these three distributions. So which means that it has guaranteed coverage. So yeah, so thank you very much. So this is the end of the talk. So let me know if you have any question or want me to go back to the previous explanation on the algorithm or the result. Thank you.
Thank you, Mi, for the talk. If anyone has questions, please, you can either unmute yourself or type in the question into the chat.
So I have a question. I'm sorry if I missed the first part of the talk. I got the time. I got the wrong time, apparently. So I don't know if you mentioned this before or not. It seems that you are only plotting upper bounds. Would your method can also be used to plot lower bounds?
Yeah. So yeah. So I guess okay. So let me answer it. So first of all, if you assume that the sample is in a bounded interval 0 and 1, so you can also so one trick to derive the lower bound is to derive the upper bound for 1 minus x. So if you haven't you want to derive the lower bound for x, then first you derive the upper bound for 1 minus x, and then you invert it to get the lower bound for x. So that is one trick. And then the other, I think another way is whether you can directly derive the lower bound for this from this method without going through the root, like deriving the upper bound for 1 minus x. That's, I'm not entirely sure actually. I will look into it. But so in our paper we had some experiment where we derive the lower bound. And in that experiment, in this experiment, we use a trick that we convert x to 1 minus x, and then we just derive the upper bound for 1 minus x.
And just to be sure, if you follow this route, it means that you have to use the probability delta. You have to use delta divided by 2, right? Because you have to apply the bounds twice.
No, you don't need to.
You don't need to?
No, so the probability that okay, so the probability that b is larger than so the mean, if you convert x to 1 minus x, so that means there's a mu of so let's say y equal to 1 minus x, so mu of y equal to 1 minus mu of x. So we just rewrite probability that b is smaller than mu x equal to probability that 1 minus b is larger than 1 minus mu x.
I see.
Which means that, yeah, I can type in the chat, but it's just equal to probability of 1 minus b larger than 1 minus mu y.
Right. No, I understand that. But if you want to plot at the same time upper and lower bound, then I would expect.
Oh, okay. Yeah. That's true. Yeah. If you have want to, if you want to have an interval with both upper and the lower, then yeah, you need to double it. That's true. Yeah.
Okay. Thank you.
Thank you.
Any other questions? Okay, if there are no more questions, I'll stop the recording. Thank you so much, Phan, again for the talk. This was a very interesting talk, very informative. The recording will be posted once ready to the AIR seminar YouTube channel. We will send out an email announcement once it's ready. And please join our next AIR seminar series. You can find, here's a link for AI talks in Boston that my colleague Vitaly has put together. So you can check the AI talks around the Boston area, and let us know if you have any questions. You can email me or Vitaly. Thank you so much.
Yeah, thank you so much for having me today. Thank you.
Thank you.